Good morning. Today we'll go to the next lecture of digital filter. But before going to the next lecture of digital filter, let me tell you today the things that will be discussed are the anatomy of a digital filter. First of all, I will be discussing regarding that related to anatomy of the digital filter. Then I'll be going to the magnitude and phase response of the digital filters. Okay, so during this I'll be explaining a bit about the characteristics of a practical frequency selective filters. Means what should be the characteristics? Okay, and later on I'll be moving on to the theorem. It's a very important theorem, Paley-Weiner theorem. Then I'll be getting to the differences and characteristics of FIR and IIR filters. Okay, so still we are on the introduction part of the filters, I think so. So let's start. Okay. So before starting, let me share the screen. But today, let me inform you one thing. Only I'll be telling regarding the note. Then only you will be looking at the note. If I don't say that follow the note, then don't follow the note, because whatever I'll be saying, everything may not be present in the note, but you should note it down on yourself. Okay. Okay. So shall we start? So I'm sharing the screen. Okay. Now we get it. So you see the heading is given: design and anatomy of digital filter. So anatomy, it's a biological word, I know, but how is it related to the filters part? It's purely engineering. So it's a different contrast. Why? You see, anatomy means study related to the features, external features. Okay. So you see, I've written, follow the note. A digital filter is a linear time invariant discrete time system with its coefficients realized using finite precision mathematical operations. Okay, finite precision mathematical operations. A linear time invariant discrete time system is described by a difference equation. You remember, I told it in the last day. I've explained, you see, in my previous note, I've given one difference between analog and digital filters. You see, and in this difference, go to point number 3. You see, I've written on the left hand side about the analog filters that they are described by differential equations. But digital filters, in case of digital filters, I've written they are described by difference equation. Okay, so there is our difference equation today that we are getting. So difference equation of the form as below. What is the difference equation? Let us see. Y of nt is equal to summation of m equal to 0 to capital M am x of nt minus mt plus summation of k equal to 1 to capital N b suffix k y of nt minus kt. Now what is this x of nt and y of nt? You see, the x of nt is the input sample and y of nt is the output sample at instant nt. Now x of nt minus mt and y of nt minus kt represent the input at some past instance. Okay, represent the input at some past instance where nt and mt is the instant, fine, and output at another past instant nt minus kt. You see, x represents the input, y represents the output. So x of nt minus mt represents the input at some past instant. What is the instant? Instant is nt minus mt. And y of nt minus kt represents the output at some another past instant. What is that past instant? It's nt minus kt. Now Now, at instant nt, the output y of nt requires the past m inputs and n outputs simultaneously. Okay. At instant nt, output y of nt requires past m inputs and n outputs simultaneously. Okay. Now, before moving to the magnitude and phase response of a digital filter, I'll be discussing something more. So listen carefully. Don't follow the note now. When I'll be telling again to follow the note, do it. You see, in terms of hardware, if you want to design a digital filter, what should be the three elements? There are certain elements, isn't it, that you should require while designing a digital filter. What should be those three elements? Those three elements, it should be the memory element. How it is related to the difference equation. Now, actually, I will be relating the hardware elements with the difference equation that I've written in my note. Okay, you see, the memory element in which the past inputs x of nt minus mt and past outputs y of nt minus kt, as well as the constants am and bk can be stored. So for this, the memory element is required. Fine. Second one, the summer and the multiplier elements. Summer means not the hot season summer. Summer means summing point, summer, that summer. Okay. Spelling is same, but meaning is different. Which perform the summing and multiplication operations for the difference equation. Fine. And third part, or the third element that is required, is very important. It is the delay element, which is needed to obtain the signals x of nt minus mt and y of nt minus kt, because you see, x of nt minus mt is the past input at some instant, and y of nt minus kt is the past output at some instant. Clear? So the delay element is needed to obtain the signals, these signals, because presently you are finding these signals in terms of input, in terms of output. So the delay element needs to find that signal. Okay, otherwise you can't insert it in the difference equation. Clear? So the above hardware elements will be required for realization of a digital filter. So in general, if we say a digital filter is what? It's nothing but a digital processor which receives input x of nt and then recalls all the past inputs and outputs stored in the memory elements. The filter then performs all the computation as specified by that particular difference equation to obtain the output y of nt. Clear? Okay, now come to the magnitude and phase response. Now again you can follow the note. You see, in the note I have written, the discrete time Fourier transform of a finite sequence impulse response Hn is given by h of e to the power j omega equal to summation of n equal to 0 to m minus 1 Hn e to the power minus of j omega nt. And this can be represented as, you see, mod of h of e to the power j omega into e to the power j phi omega. Now, what is this phi omega? Phi omega is the phase response, and mod of h of e to the power j omega is the magnitude response of the digital filter. Clear? Now, we have to find the magnitude and phase individually. Okay. So magnitude m of omega equal to, you see, mod of h of e to the power j omega. So mod of h of e to the power j omega can be split as the real part of h of e to the power j omega square plus imaginary part of h of e to the power j omega square whole to the power half means anything magnitude. How we find? You see, if there is a complex complex number a plus ib, and if you are asked to find the magnitude, what you do? Root over of a square plus b square. This is the magnitude. Fine. So same case. Mod of h of e to the power j omega is treated as real part and imaginary part. And these two are the two individual components. So square of the real part plus square of the imaginary part, total under root. So total to the power half everything. Clear? Now come to the phase response. Phase response, obviously a plus ib's phase response is what? Tan inverse of b by a, isn't it? So same case here also, tan inverse of imaginary part of h of j omega by real part of h of j omega. Clear? You can just correlate. It's very simple. Okay. Now come to the delay. Phase delay, group delay. Phase delay is what? It's denoted by tau. The Greek alphabet tau. Phase delay is denoted by tau suffix p. Group delay is denoted by tau suffix g. So tau p is equal to minus of phi of omega by omega, and tau g is equal to minus of d of phi omega by d omega. Okay, it's the derivative. Actually, group delay is the derivative of the phase delay. Here. Now, before moving to the Paley-Weiner theorem, I'll be discussing something more. So listen carefully. If you want, you can write also. You see, linear phase filters. What do you know about them? Linear phase filters. Any idea? You see, linear phase filters are those in which the phase delay and group delay are constant. Constant means independent of frequency. That's why linear phase filters are also called constant time delay filters. Linear phase filters are also called constant time delay filters. Okay, constant time delay filters. Clear? Now, you see, ideal filters, if you want to speak about the characteristics of practical frequency selective filters, then you should know something, that ideal filters are non-causal and hence practically unrealizable for real-time signal processing applications. Now in practice, h of omega cannot have an infinitely sharp cutoff. Obviously, it cannot have, no, from pass band to stop band. It is not absolutely necessary to have an ideal filter response in most practical applications. So, however, it is possible to realize causal filters that approximate the ideal filters as closely as desired. Okay. The magnitude need not be constant in the entire pass band of the filter. Small amount of ripple in the pass band may be allowed. Ideal cases, actually, these ripples and all are not present, but in practical cases, it should be allowed. Otherwise, you can't get proper answers. Okay. Also, it is not necessary that the magnitude response should be 0 in stop band. In ideal case, the magnitude response, obviously, it should be 0 in stop band. Stop band means what? You are not allowing the frequency. So, obviously, no magnitude response. But here, in case of a practical application, there can be very less magnitude response in the stop band. A small amount of ripple in the stop band may be allowed. So the transition band or the transition region of the filter is defined as frequency band, over which the transition of the frequency response from pass band to stop band takes place. Clear? Now, in filter design, what we need to specify, there are 4 things. Listen carefully. One is the maximum tolerable pass band ripple. One is the maximum tolerable stop band ripple. One is the pass band edge frequency, and The fourth one is the stop band edge frequency. Clear? So four things. Again, I'm repeating. One is the maximum tolerable pass band ripple. One is the maximum tolerable stop band ripple. Third one is the pass band edge frequency. And fourth one is the stop band edge frequency. Clear? Weather is very bad today. You can hear the thunderstorms. Okay, come to the Paley-Weiner theorem. Again, you can follow the note. You can start following the note. So it's a very important theorem basically. It states that if Hn has finite energy and Hn equal to 0 for n less than 0, then integration minus pi to pi mod of ln h omega d omega less than infinite. If you can convert the theorem, conversely you can say that if h of omega is square integrable and if the above integral is finite, then resulting frequency response is, you see, h of omega equal to mod of h omega into e to the power j theta of omega. Now, what is this h omega and theta omega? H omega and theta omega obviously magnitude and phase response. Clear? Now, before moving to the FIR filter advantages, what do you understand from this Paley-Weiner theorem? Again, stop following the note. Listen carefully. What do you understand from this Paley-Weiner theorem? You see, from Paley-Weiner theorem, we can conclude that the magnitude response cannot be zero at some frequencies, but it can be zero over any finite band of frequencies. Since, why it can be zero over any finite band of frequencies? Since the integral then becomes infinite. Since the integral then becomes infinite. Thus, it follows that any ideal filter is non-causal. Very important term. Remember, again I am repeating. The magnitude response h omega cannot be zero at some frequencies. There are certain frequencies where h omega cannot be zero, but it can be zero over any finite band of frequencies. Why? Because the integral becomes infinite. Okay, integral becomes infinite, and from here we can conclude that any ideal filter is non-causal. Any ideal filter is non-causal. Okay. Okay. Now, in the note, you see FIR filter advantages. I have written directly, but before knowing the advantages of FIR filters, let me tell you something about FIR and IIR filters. Okay. Listen carefully. You see, digital filters, obviously, there are two types. One is FIR, finite impulse response, and the other one is the IIR, infinite impulse response. So, FIR filter, what they are also known as? They are also known as non-recursive filter. Whereas IIR filters is also called recursive filter. This you already know from lecture 1. Both of them have certain advantages and disadvantages. Good. Now, on which basis will you select FIR filter or IIR filter? You see, the selection of an FIR or IIR filter depends on the nature of the problem and on the specifications of the desired frequencies. Nature of the problem and on the specifications of the desired frequency response. In practice, an FIR filter is employed where there is a need for linear phase characteristics within the passband of the filter. If linear phase characteristics is not required, either FIR or IIR filters may be chosen. Clear? However, an IIR filter has lower side lobes in the stop band than a FIR filter having the same number of parameters. Okay, so therefore, if some phase distortion is either tolerable or unimportant, an IIR filter is preferable as its implementation involves fewer parameters. Clear? Requires less memory and has lower complexity. However, in many digital processing applications, FIR filters are preferred than IIR filters. So now let us know some advantages that I've already written in the note. You can follow. FIR filters are always stable. They have exactly linear phase characters. Design is generally linear. FIR filter startup transients have finite duration. I've written only 4. There are many more. You can listen. FIR filters can be realized efficiently in hardware. FIR filters are free from limit cycle oscillations when implemented on a finite word length digital system. Now, apart from these advantages, don't think there are zero disadvantages. There are disadvantages. Okay. So what are those disadvantages? You see, their memory requirement and execution time are very high. Moreover, the implementation of narrow transition band FIR filters are very costly. Implementation of narrow transition band FIR filters are very costly. Okay. Implementation of narrow transition band FIR filters are very costly. Here. So now, come to the differences between FIR and IIR filters. So I've written how many? 6 differences I've written. There are many more, so you can see the book. But major differences are these. You see, IIR filters, they are unstable. FIR filters, they are stable. Point number 2, in IIR filters, they do not have linear phase response. For FIR filters, they have exactly linear phase. For point number 3, they are less flexible. Here, in FIR filters are flexible. Round of noise is more in case of IIR filters. For FIR filters, the round of noise is less. Frequency transformations are well established. These are not available for FIR filters. For IIR, they are more efficient in terms of computation time. For FIR filters, they require more processing time. Okay, so there are many more differences here. Many more differences are there. Like analog filters can be easily transformed into IIR filters. In case of FIR filters, analog filters cannot be transformed directly to FIR filters, but they can be directly transformed to IIR filters. Then delay-free loops arise in variable filtering, causing instability. So that I've written the first point in IIR filters that they are unstable. It is due to this reason. Delay-free loops arise in variable filtering, which causes instability or instability. For FIR filters, the variable filtering can be easily implemented using cosine transformation. Okay, using cosine transformation. Here. So more differences are there, like I'm telling. Facility for optimization of IIR filter is not available. You cannot optimize IIR filters because obviously they are already having fewer parameters. DFT relations facilitate certain optimization procedures for FIR filters. If you use discrete Fourier transform relations, they can provide you certain optimizations for FIR filters. Okay. Then for IIR filters, the implementation requires more care. You have to be very careful while implementing an IIR filter than a FIR filter. But FIR filters realizability is always guaranteed. And so you can easily implement a FIR filter. Okay, so these are certain differences, and that's all for today. So we end up our lecture here. Thank you.